First, we gotta understand what is a wave. So the definition of wave is wave carries and transfers energy without the transferring of matter. Okay, that's what wave is. So I'll write it down. Wave, you can write it down as well if you want. Wave is a vibration pattern. It might not be in the notes, okay? That transfers energy. Without the transfer of matter. Hold on. So when I'm talking to you guys, the sound wave traveled to an ear, but the particle did not move, right? Yeah, so particle just vibrates in there, okay? Yeah, and then according to the direction it vibrates, then we have two types of wave. One is transverse wave, one is longitudinal wave, right? Okay, then you say longitudinal wave. Transverse wave. Okay, actually, I'm going to leave you guys some homework to do as well. Instead of just telling you what it is, writing it down for you, I want you guys to go back and find, okay, what is transversal wave, what is longitudinal wave, because that could be a question in your test. And there are questions where like, you need to like understand things using the concept to analyze it, but a lot of the things you just need to remember it. For example, right? They say, oh, the question might be, okay, explain what does it mean by transverse wave? Then you have to say, well, it's the vibration, and that is going to be perpendicular to the direction the wave travels, right? Yeah, don't write it down. When you go home, you can go look for it, okay? Yeah, and what is longitudinal wave? I mean, here, it's all in the book, okay? All right, and then the typical example of transverse wave is going to be light wave. That's the first one, right? And then the second one over here says longitudinal wave. So sound wave is a longitudinal wave, vibrates like that, right? Okay, and then over here, we have two graphs. So the two graphs, one have time over here, and one have a position over here. Okay, and then over here, it's all going to be called displacement, which is y. This is going to be displacement. So they're going to draw something like this. So when we draw a wave, it's best to make the scale over here evenly spaced out like that. Draw the scale first, and then we can draw the wave onto it. Like that, right? Okay, and then we're gonna figure out, okay, what is the everything over here? So over here, this is gonna be the amplitude. Same over here, this is gonna be the amplitude. Okay, and then horizontally, if this is time, and what is this point over here? The time for one wave. What is the concept of time for one wave? The time.
Oh. No.
Time is going to be period.
Oh.
Okay, so this graph here, it tells you the period t. Right? And then this one over here, it tells you the wavelength.
Where? Which one?
This point here. Because this is a position graph.
Yeah.
So position, if the wave is like that, then this will tell you the wavelength, yeah. So according to which graph they give you, it could give you, even though the shape look exactly the same, The y-axis is the same, but then the horizontal axis is different. So this one is going to be a wavelength, and this is going to be a period.
So that's a period graph, the other one is a wave graph.
Yes, yes. Yeah. So how is these two like things? How does they work? If we look on this side, you see, according to time, the object is vibrating up, vibrating down, vibrating up, vibrating down. Does that make sense? So we are looking at one particular particle over a period of time. Right now, it's at this time it's sitting over here, right? And then the next second it has moved to here. Say 1 centimeter, 2 centimeter, 3 centimeter, 4 centimeter, 5 centimeter. Does it make sense? And then it's coming down 4 centimeter, 3 centimeter, 2 centimeter, 1 centimeter, 0. So it's according to time, it's moving up and down. Okay? But this one is position. If its position is at this exactly moment, I'm taking a picture. What does a wave look like? Think about you look at the water, a rock throwing into the water. And at the moment right now, you see the wave is like that. Does it make sense? So this is what it looks like at a moment. This is what one particle looks like over a period of time. That's why this one you can find period, this one can find wavelength. Okay. Okay, and obviously wavelength, this from here to here is wavelength as well. From say this to here, that is wavelength as well, right? Wavelength is as long as the two corresponding points. Here is also wavelength, right? Yeah, same with period. Period could be this top to this crest, could be this point to this point, as long as they're corresponding 2 points, okay? Or from this one to this one here. Okay? Yeah. So now, the next thing is, well, what is their definition? It tells you period is the time taken for the wave to travel for one length, right? And frequency is the number of wavelengths passed through every second. So these two are the opposite concept. So then we have this equation. I'll write it at over here. So period equals to 1 over frequency, or frequency equals 1 over period, right? And then the key thing here is the unit. So for period, it's going to be using second, and then frequency, the unit we used is going to be hertz. Okay, and then over here, we're going to quickly talk about the conversion. So sometimes you might have millisecond, M. So M is milli. Milli is 10 to the power of negative 3. So if you have millisecond, say you got 50 millisecond, then it's going to be 50 times, right here, okay, example, say T equals 50 millisecond. And that equals to 0, or equal to, 50 times 10 to the power negative 3 seconds. Right? Okay. And then we got something called kilo, okay? Which is like kilogram. That's 10 to the power of 3. Okay, example, the frequency equals to, say, 50 kilohertz. So that's going to equal to 50 times 10 to the power of 3 hertz.
Do we need to know this?
Yeah, you need to remember it. Yeah, I wouldn't tell you.
So
Yeah.
all you're saying is like if they give a measurement in that, that's just what it means. So that's just what 15 billion.
Yeah, instead of writing like 30 on the back, they just say kilohertz. Yeah, or say if you got a really big value, so if we talk about like light, sometimes we might have megahertz. Okay, what's mega? It's like when you have a cell phone, right? So yeah, that's 10 to the power of 6. Sometimes we use megahertz. Back in the days when we have an MP3 player, have 128 megabyte, right? That's how big it is. Okay, so one song, like a simple format, is going to be like 6 megahertz or megabyte. Okay, so 10 to the power of 6. So now let's say frequency, if frequency is equals to 50 M hertz. Look, this is a capital M, right? If it's a capital M, that means it's mega, so it's 50 times 10 to the power of 6 hertz. Cool? Okay. And then here comes our most important equation in wave, which is V equal F lambda, right? So you guys all know that. Okay, and then V obviously is speed of wave, meter per second. F is frequency, which is going to be hertz. Lambda is wavelength, which we use meter. Okay, and then over here, I want to emphasize, sometimes there's always some hidden information over there you will need to watch out for. For example, if they talk about speed of light, how big is it?
Isn't it 3 point something?
Yeah, 3.0 times 10 to the power 8. Sometimes you don't see there's speed of light, but it's actually given to you in the information sheet, okay? Or say speed of sound wave, it might be 330 meter per second. That is the hidden information. It might be given to you in the question, so you need to be careful.
So what would they call it? They would call it speed of light? Or?
Yeah, the speed of light, or they will give it to you, yeah.
Okay.
Yeah, so I'll write at the bottom, I'll say, okay, speed of light in vacuum.
What is it normally used for? Give me like an example.
Huh?
What would it be used for? Like,
Okay, I'll write it down first, and then I'll tell you how we're going to use it. Okay? Yeah, it's in the resource sheet. Yeah. I just want to mention it here because sometimes you might see a question, oh, what do I do? But, oh, there's actually numbers that's in the resource sheet, okay?
will you get marked down for using the wrong units, or is it fine?
If the question specifically asks you to write the right unit, then you need to use the right unit. The problem is if you don't use the right unit, sometimes you'll get a wrong answer. Yeah, if you get a wrong answer, and then they will punish you. But if you just, in general, you have the correct answer, but you write the units wrong, and normally they don't really care, unless the question specifically asks to get the correct unit.
Oh, yeah.
Okay? Yeah, okay. Speed of sound in air is 330 meter per second. Yeah. Okay, so
What does the last unit say? The last, is it 300
meter per second. Okay, and then well, why is this important? Not only that you need to be able to calculate it. For example, they tell you the wavelength of a red light is 480 nanometer, for example. Okay, okay. So over here, I will add another one, saying you can have a nanometer. 10 to the power of negative 9. Okay, I'm just squeezing another little one, okay? And then there's another one called micro. Micro at level 2, you don't use it very much, but at level 3, you use it quite a bit. That is negative 6, which is a symbol look like this.
So we need to know all of this.
You need to know all of this, yeah.
Do we need to remember but in the question they'll have this, like, the negative 10, right? They would like...
Depending on the year, they're making NCEA easier and easier, now they tell you, but you always needed to remember it. So I'm not sure if the marker is gonna make it easy this year, say, hey, when I use micro, I'm actually gonna convert that for you, or is they expecting you to remember, okay? But I will expect you guys to remember it.
So all I remember is like the number, so like if it's negative 3 or
Yeah.
2 pounds.
They will show you this symbol.
Yeah.
They will say 8 meter, 20, and then
That's when we write the answer. When
yeah, no. When you go into this equation, what number do you put there? You can't put 20 there.
3 times 10.
Yeah, you got to use 20 times 10 to the power negative 6 in there, and then you calculate frequency and get a correct frequency, right? Yeah. So say this. They tell you now. They tell you this is 650, say nanometer, right? And you need to know it's 460 times 10 to the power negative 9, and then you know the speed is gonna be this light speed. Then you can calculate frequency, right? Yeah. Okay. So not only that is important, and next thing, over here you might have a lot of like questions like this. For example,
Sorry. Are there any goals for SP2, SP1 for electricity? No?
no, they are here for waves.
Hmm?
They're all here for waves.
I know they're here for waves. I just got late, so.
Oh, that's fine.
Okay.
You can just maybe do it later.
Yeah,
If you want to finish, they might want to do electricity.
Okay.
Yeah.
Okay, thanks.
Okay. Okay. So now let's quickly have a look. So let's say this. Yeah. In later we have something called refraction, right? So it means this. Okay. If you have a wave, right now the wave is traveling in air, and then it's gonna travel in water, right? And we know how this is gonna change in speed, right? But well, why does it change? Well, why does it change direction? Well, that's because the speed is changing. Because the speed of a wave is dependent on the medium, right? So if the speed is gonna slow down or speed up, but what's not changing?
Frequency.
Yeah, frequency is the one not changing, right? If frequency is the one not changing, if we look at this equation, if the speed gets bigger, what happens to wavelength? Yeah, wavelength is gonna get bigger. If speed gets smaller, wavelength will get smaller, right? Okay, see, a lot of explaining question is actually just an equation question, right? It's just another way of testing you the equation, yeah. Say this, if you're traveling from a glass into air, for example. Now, the speed is gonna speed up, right? If it's speed up, it's gonna start to bend forward, right? Because it's gonna start to speed faster. So the gap will wavelengths get bigger because say frequency don't change, speed increase, and the wavelengths will increase, right? Yeah, so that's why this equation is like really important, okay? Okay, so now next one. Okay, next one, this part, I don't want to spend too much time talk about it. So have a look of the behavior of wave. You got the picture, say there's crest, there's trough, right? And there's wave. So sometimes they call this the wave front. Well, that's a wave front, and that's another wave front. These are representing the crest, right? Or rarefaction. So obviously that's gonna be your wavelength, right? Okay, so that is in there, and then sometimes they will draw a line, and then that will be the wavelength, right? So that is just a wave going forward, right? Instead of a circular wave going outwards. Okay, that's easy. Okay, and then when you have this situation, when you have a two rope situation, say one situation is if you have a light rope coming to hit a heavy rope. Right? Okay, and this is just purely about remembering what happens. Okay, so here they will tell you speed is bigger in light string. Okay, if speed is light string, when it comes back, it's going to be inverted. But the wavelength is going to stay the same. So I'm going to make sure that my wavelength is the same. But then the amplitude is going to become smaller because amplitude is representing energy. Some energy is going to be lost. Does that make sense? Okay, it's all in that picture, okay. So wavelength becomes smaller, but I'm keeping the wavelength the same. Oh, sorry, amplitude is smaller, wavelength is still the same. Okay, so now we're coming to this side. This is called a 180-degree change of phase, right? So I will also draw this one over here as a comparison. Let me draw this as a stick string. Say this wave is going this direction, what happens? Again, the wavelengths don't change, but the amplitude is going to become smaller because some energy will be lost it, right?
So wavelength doesn't change no matter what, right?
If the medium don't change, then the speed don't change. If the speed don't change, then the wavelengths don't change. Okay, so it actually comes from that. So that actually in the notes over here is actually written on the bottom over here. Okay, and then what happens with this one is this one also has smaller amplitude, and because the speed has slowed down, if speed slowed down, V equal F lambda. If speed slowed down, what happened to wavelength? Yeah, wavelength need to slow down. So this one will have a smaller wavelength. And also the amplitude will become smaller because it has less energy, right? The original total energy is going to be shared between these two. And also this will be much closer compared to this one because the speed is slow, right? Okay, and then same thing, we're going to draw this one. This one is going to travel faster, so this has reflected back to here already. Well, this one will travel a lot further out, right? So this one travel all the way to here. And then because V equal F lambda, the speed is become bigger. If speed become bigger, what happens to wavelength? Yeah, increase as well. So over here, I need to draw a bigger wavelength. Sorry?
Yeah, what's the difference between thick and thin?
It's just the speed is going to be bigger in the light string, a heavy string.
Okay, so the
This is a heavy string. This is a light string. So this is fast speed. This is slower speed.
okay.
So this is about reflection of wave and transmission of wave. Okay, so what happens when wave come to a boundary? Some of it will be reflected, some will pass through into the boundary, right? And then there are all sorts of situations, but we are dealing with one particular situation at level 2 physics. It's when you have a heavy string and a light string. What happened to this? Yeah.
So
Yeah.
it doesn't tell you if it will tell you if it's going first through the heavy. Because sometimes it can go first through the heavy, then into the light, right? Or is it always from light to heavy?
For this type of question, they only test you like this. That type of question you were talking about was a block. We were talking about light. Light coming to that and then bend again, become parallel to the original one. I think that was the question you were talking about. Okay, we'll talk about that one a bit later. Okay, so this you just need to remember again. That is in the notes over here at the bottom over here, right? Yeah. Okay. So okay. So next one. So next type of question is when you have a poses. So if you have one pose coming, this one coming this way, this one coming this way, and when they meet together, they're gonna become like this, right? And when they move away from each other, then they become this again. So this is called a constructive interference, right? Okay, and then over here, we don't have a lot of time to go through every type of question. I mean, if they want to test you harder, they could make you say, oh, every second it moves like forward like 1 meter, and 1 meter is 1 square, and then they will say, okay, after 5 seconds, draw the shape of the wave. Then you're gonna draw, okay, this wave is here, now have this shape. Okay, the other wave is over here, now have this shape. Now some of them are gonna cancel out, and some of them are gonna be adding together, right? So you should have some of the questions in your book about it. Okay. All right. So next part, and next part is we have something called 2-point source interference pattern, right? So 2-point source interference pattern is when we have this thing, a circle, a circle, a circle, and then a circle, a circle, a circle, a circle like that, right? You guys still remember that? Or another situation you have is you might have this. So you might have a few waves coming this way. And then it start gonna diffract. Right? Okay, and then over here, the key thing is you need to find out, well, what is going to be the path difference. Okay, so path difference is, well, let's call this S1, S2, and we're going to use a point as an example. Say this is a P point, okay? So the path difference is going to equal to PS2 minus PS1. Okay, and once you calculate the path difference, then you're gonna go compare it with wavelength. If path difference equal to n wavelength, if path difference equal to n minus 0.5 wavelength. Okay, if that happens, we got something called constructive interference. N is just a number, 1, 2, 3, 4, or 0, yeah.
So in this case, looking at you, that's a constructive interference?
This one we don't know.
Oh, you don't know yet?
We have to calculate, yeah.
Oh,
So you put the number in. So for example, if the next line coming like that, yes, that would be a constructive interference because the P point is where the two crisps is gonna meet.
Oh, okay.
Yeah, but I have to calculate it in order to know.
So when you get the answer, let's say, I don't know, I don't know what the answer would be, but like,
Yeah.
how would you know if it's constructive or destructive?
Let's say if I calculate it equal to 3 wavelengths,
Oh,
I need to compare the path difference to wavelength. Say my path difference, I minus these two numbers to each other, I get, say, 3 meter. Okay? Say path difference equals equal to 3 meter, right? And then they tell you the wavelength is going to be 1 meter. So then you know your path difference is 3 times of this wavelength, right? So now you get path difference equal to 3 wavelengths. If path difference is 3 wavelengths, which criteria is it matching? Okay, it's matching this one here. So then you know it's going to be constructive interference.
how do you know? How does it look like if it's a destructive interference?
Say you calculate path difference equal to 2.5 wavelengths.
Okay.
Yeah, or 0.5 wavelengths, or 1.5 wavelengths.
Oh wait, so if it's a 0.5 number, then it's a destructive.
Interference, yes. Yeah.
Okay.
Yeah. So you just calculate and then you go compare it. Yeah. Okay, so now, and then constructive interference over here, we have a few names we need to give it. So we got a keyword, we call it antinodal. Antinodal. And this is called nodal. Antinodal line. This is called nodal line. Okay, and then constructive interference is going to have big amplitude. This is going to have 0 amplitude. So this 2 wave going to arrive in phase. This one is going to be 180 degree out of phase.
It's not that the whole thing is a constructive. It's only a couple points that would be, right?
Yeah, we're only talking about, we're analyzing the point over here. So normally what the question will ask you is the question will give you, say this is a dam, and then these are the water coming from the ocean, right? And you are on a boat and you're sitting at this position. They ask you to say, okay, how would your boat feel, right? And where do you want to park your boat? If your boat is parked on this thing over here, it's going to have a big amplitude. So your boat will be rocking and down a lot, right? Where if you park your boat at a nodal line, and then you will be able to have like 0 amplitude, so your boat will be quiet. Does it make sense? If that's water wave. If it's sound wave, over here will be very loud, and then over here will be like very quiet, okay? So say the middle line over here, that's gonna be a very loud sound or very bumpy up and down. You got a nodal line, that's your antinodal line, another antinodal line, say another antinodal line like that. This is all constructive interference, okay? And then you call your destructive interference like that. That's gonna be your destructive interference in the middle. Okay. Do you guys have notes for this?
Yeah.
Okay. I'll quickly show you guys a picture of it because it seems like you guys are not too sure about this. Let's see. I think I might have taught this during lockdown. If it's during lockdown, I've taught it, so I will have some notes about it.
Oh yeah.
Oh, here. Are you guys familiar with this diagram? Okay, I can take a picture. That's just a picture I copied from Google, and then I just draw it on it. Yeah, so this is source 1, and this is source 2, right? And they're forming this pattern, right? And we're analyzing this pattern just like we did before, okay? So, and then in the middle, you will have a constructive. The red one are constructive lines, and then the blue one are the destructive lines. So if you're sitting on a destructive line, you will have, your boat will be like not moving, right? If you're sitting on the red one, your boat will be moving, right? But however is, we don't know where the pattern is, right? The question is just gonna give you a few numbers you need to calculate. And then you will say, okay, so the P point is the number give you, they tell you this distance is 10 meter, they tell you this distance is, say, 12 meter, and then you calculate, you minus those two, you say, hey, the path difference is going to be 1 meter, right? And they say, okay, that equals to 1 wavelength. If it equals to 1 wavelength, where is it? It's going on a constructive line, which is the first constructive line.
So if it was like 1.5.
If it's 1.5, it will be over here. Yeah, that's going to be this destructive interference.
Wait, how do you know it's that one and not the other side?
It could be this side.
Okay.
Yeah, you just look at which number is bigger.
Okay.
Yeah, the question will give you a picture. Okay, yeah, and then over here I write it very carefully here. See which one? This is 1 wavelength, 1.5, 2 wavelength, 2.5, and just like that. Okay. So that's 2-point source interference pattern. Honestly, like that's like a really most difficult question over here in this topic, and they might not even test it because this is not the most important thing. Because at level 3, they will test you this again, so that they might save it for level 3 to test you. So I would say if you maybe focus on like other important things first and then come here, because there are some questions like they have to test you. They always test you every year, like Snell's law, like critical angle, total internal reflection, like something like that, right? Yeah. So and then after you finish that, you're like, okay, now I'm ready to tackle these more difficult questions and come back to here. Okay. Also about revision, like don't just do questions. If you just do, the point of doing questions is to figure out what part you don't know. Okay? If you don't know how to do a question, you look at it 100 times, 2 hours, you still cannot do that question. So the key is to go back to the notes and try to understand the concepts. If you can understand the concept and then you come back, look at the question, then the question starts to make sense. But if you don't remember this, for example, if I ask you what is diffraction, and you have no idea what diffraction is, then forget about doing all the questions. You've got to go back to the notes to read the notes and remember what is diffraction. And then I can use diffraction to analyze this question. Does it make sense? And that's super important. That's why I always emphasize, like, why do we spend so much time writing notes down? Because notes are important, and that's the key thing, right? Say if you don't know this notes, if you don't know what this past difference, first, if you don't even know what past difference is, forget about it. Then you will not be able to do any questions regarding to 2 points interference pattern. Does it make sense? So you've got to go back. Okay, when I read this, can I understand what does this mean? Okay, when I look at this picture over here, can I figure out what is happening to these questions? If you're not too sure, you got to look at the notes, and then maybe you can go onto YouTube and to search someone teaching this. Okay, there's heaps of video like about this kind of thing as well. Okay, all right. So now let's move on to the next one. Okay, strategy is the most important. So the next one is gonna be electromagnetic spectrum. So I'm just gonna quickly show you guys because I believe I have it over here. Sorry, that's a level 3 notes. Oh, I just use Google to find one. So electromagnetic spectrum. Okay, so this is electromagnetic spectrum. So we call this electromagnetic wave, right? Another name for electromagnetic wave is just light wave. These are the different types of lights, okay? except only one of these light that we can see it, which is what we call visible light, right? So visible light is the ones that we can see, and all these other ones we cannot see, okay? Ultraviolet, some people say, oh, that is a violet, has a color of violet. It doesn't have a color because we can't see it, okay? The ones we can see is the violet. The violet, we can see it, okay? So it's past violet, okay? And then X-ray, gamma ray, infrared, microwave, and radio wave. And you sort of need to remember like the rough order of it. I recommend everyone to remember the order because sometimes they might make comparison. They might have this wave and the other wave. They make a comparison about it. Sometimes you might need it, but again, it all depends on the examiner. If the examiner says, well, I will tell you the radio wave have a longer wavelength than the microwave, and then it will be easy for you. Does it make sense? Okay, so what we need to know over here is to this side, you got high frequency. And to this side, you got long wavelength. Okay, and then again, we use V equal F lambda. If the frequency is high, and this time the speed don't change anymore. Because previously we're changing the speed, right? When we talk about refraction. If the speed is not changing now, high frequency will give you small wavelengths here, right? And then on this side, V equal F lambda. Speed don't change if the wavelength is long and now the frequency is gonna become small. So longer wavelength is smaller frequency. Higher frequency is faster. It's bigger wavelength. Smaller wavelength.
So wait, how come the speed doesn't change again?
That's because that's speed of light.
Oh,
Yeah. These waves all got the same speed.
Okay.
Yeah. So, and this, remember at the very beginning, I was like, oh, there is a hidden information, 3 times 10 to the power 8, right? You might think, oh, that's a bit silly. Of course, I know there's a hidden information there. But you might get confused because the question might tell you, oh, a microwave have a frequency of this. But then do you know that is also the speed of microwave? That is the trick the student will encounter because they'll be like, oh, I don't know the speed of microwave. What they don't know is actually, well, the speed of light is the speed of microwave because microwave is a light as well.
So everything that's there, it uses the speed of light?
Yeah, because they are light. These are the different lights. Okay? So, and then these ones, gamma ray will have more energy. The one this side will have a bit less energy. Okay, yeah. Okay, so, and then the other one you need to remember is the visible light. You need to remember the order. Okay, so you got red, orange, yellow, green, yeah, green, blue, then you got indigo, and then you got violet. Yeah, that's a rainbow color, yeah. So the rainbow color are the visible color that we can see, right? And then from, again, this side is long wavelength. If it has long wavelength, guys, it will have small frequency. Okay, and then this side, you will have a short wavelength. High frequency. Hey guys. Yeah. Yeah, you can, yeah. Well, how come all of a sudden there's so many people?